Sarah Jensen, Technical Editor with Power and Motion, and today I'll be speaking with Andrew McMahon, Managing Director of Technical Services, about the company's new high voltage thermal management system for electric vehicles. So just to kind of maybe start, could you maybe provide a bit of an overview of how or why the development of Technical Services' new high voltage thermal management system came about, and maybe why the company chose to develop a high voltage system as opposed to a low voltage system?
Sure, thank you. It built on the low voltage work that we've been doing in the low voltage systems we've been providing for many years. And what we found is that we see ourselves really in a second or third phase of a new market and the iterative improvements that come with that. We've really seen radical changes moving from IC engines to EV battery and fuel cell powertrains. Initially, the drivetrains for EVs wouldn't have been possible without high voltage batteries and motors. So then when you look at a system level approach, the next big power consumer or user of amps within the system is very much the cooling system. Early EVs were typically much smaller platforms. They were battery operated, and the cooling demand could be managed. The modest flow rate and the modest heat rejection from a smaller EV platform could be done with a low voltage system. But we see as the market has expanded for wider use cases, and ultimately the size and capacity of the machines have increased, so has the cooling demand. So it's really driven the development of HV components.
Mm-hmm. Okay, so what are those new cooling demands that you guys are seeing, and kind of how does the system help with those?
Sure, the cooling demand on an EV circuit as a whole is much lower temperature on the fuel cell, the battery, the drive motor and power electronics. There's such lower temperatures compared to traditional IC engine cooling, and this creates a lot of challenges. It drove the increase in product development along the component line to deal with increased flow rates, increased heat rejections that come with these larger platforms. This impact we really see magnified considerably on the cooling system, especially when we look at fuel cells and the associated heat rejection of a fuel cell compared to a battery platform, which has far less heat rejection as a whole.
Okay, interesting. So why does the fuel cell system have a higher heat rejection than the battery?
So the fuel cell producing energy in real time, running at, in some cases, 50% efficient. So if we're producing 100 kilowatts of electrical power, it's also rejecting 100 kilowatts of heat into the system. Whereas the energy model on a battery system is very much charging over a longer, slower period of time and discharging. Whereas the power available from a fuel cell, it's that constant heat rejection to the system, which needs to be dealt with in real time.
Mm-hmm. Okay. All right. So could you maybe go into a little bit more about the high voltage thermal system, and maybe what are some of the components involved and how they all kind of work together to provide appropriate thermal management?
Sure. So specifically within the vein of thermal management, the key components really are the highest power consuming components in the cooling loop, and they're the pumps and the fans. Also the cooling modules, where we have multiple fans on one or many heat exchangers. But pumps and fans alone are not what I consider thermal management. They're very much key components, and that thermal management requires a system level approach, starting with initially the cooling system architecture. Once the cooling system architecture is correct, then we can certainly start to do product level selection, and then in comes the high voltage components with an architecture that's been designed for those components. So pumps, for example, a pump in its purest form provides a flow of coolant around the system, and the system the coolant is flowing around is then seen by the pump as the obstacle to that flow. And therefore, any pump selection must be made with the entire cooling loop in mind, having addressed first the cooling system architecture. Likewise, fans are an integral part of the cooling system, They increase the mass flow rate of air across the heat exchanger, aiding cooling when we're rejecting to ambient air temperatures. Most EVs will have multiple cooling loops. They will also have multiple fans on some of those cooling loops. So when we then make a component level improvement from a low voltage to high voltage, that improvement is magnified by component levels on the whole vehicle, which is multiple cooling loops and multiple products on each cooling loop. So the benefits are 4, 5, 6, 7-fold, depending on the complexity of the installation.
Okay, all right. So I know you kind of touched on this a little bit already, but maybe what are some of the key aspects that need to be considered when developing thermal management solutions for electric, hybrid, and fuel cell powered vehicles?
Sure. So we always start with the cooling system architecture, and ultimately it's what is the cooling fluid? When we have the right fluid, then we look at the components in the loop, the layout of those components, comparing scenario A to scenario B, many components in parallel, components in series. We look at scavenging waste heat from one loop and putting that heat into another loop wherever possible for waste heat recovery. And then ultimately, once the overall architecture is right, then it drills down to component level, whether those components are existing components that are in the market already, or whether it's new product development in order to realize that architecture that you put together. It's very much at the moment, as the component availability isn't what the market would really want it to be, it ultimately comes to an element of compromise on the architecture level. So we have an ideal loop that we would like to have, but the components are not available. So there's sometimes an element of compromise, and these compromises, as we see the months and years go by, will be less so because the products have been developed to release the potential.
Okay, all right. So then what would be, and again, I know you kind of touched on this before, but like what would be some of the differences between the cooling needs for high voltage systems versus low voltage systems, and how will technical services system help meet those needs?
Sure. So at a purest level, a high voltage cooling system is going to be far more efficient than a low voltage cooling system. And those efficiencies are not just on a single component basis, it's system wide. You can reduce your need for DC-DC converters, for example, which are costly, take up space and have a certain efficiency. But it also reduces the cooling complexity, because many of the additional power electronic circuits that are providing the power for the low voltage components then have their own cooling requirements as well. So fundamentally, the high voltage cooling loop is simpler than a low voltage cooling loop. It's more efficient than a low voltage cooling loop. And then as we move forward, what we see then is traditional heat exchanger may have 4 low voltage fans, whereas high voltage enables us to run a larger diameter fan with a higher power motor. And then we can use the fundamental efficiencies of a fan, where if we run the largest diameter fan we can at the slowest possible speed, we'll get the best efficiency from it as a fan, rather than many smaller fans running at a faster speed. But we also start to reduce noise on the application as well. So the efficiencies are both in terms of electrical, in terms of architecture and real estate on the vehicle, but also in terms of expanding the use case into higher ambience, higher heat rejections, and reducing other emissions such as noise from the cooling system.
Okay. All right. So what types of applications would this system be beneficial to be used in?
Sure. So in time, I hope to see HV components across most mainstream EVs. However, the phase we're in at the moment, we really have to go for the low-hanging fruit. And these are the higher heat rejecting systems and the systems that need to operate in really high ambient temperatures. Currently, we're promoting high voltage cooling systems and high voltage thermal management, specifically at the fuel cell applications and the fuel cell market, and effectively commercial vehicle sizes and above. So your on-highway truck, bus, your big construction equipment,
Mm-hmm.
anything that's powered by typically 100 kilowatt and upwards fuel cells. But that's not to say that in time, the product range won't be more appropriate for everybody.
Okay. All right. So then just to kind of wrap up the conversation, what are maybe some of the impacts you guys are seeing from electrification and on thermal management system development, and maybe how do you see the trend progressing in the coming years?
We're very excited about electrification. We have seen such rapid growth in the number and complexity of customer projects, and this is from both new and existing customers. It's really resulted in an accelerated investment in people, in systems and equipment. We're forecasting really exciting growth through until 2030 and beyond. It's a very fast-paced sector, and it's a very exciting space to be working in at the moment.
All right, great. Well, thank you so much for taking the time to speak with me today and provide some insight into the high voltage thermal management system you guys are developing.
You're very welcome. Thank you very much for having me.